Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 53. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with condition required for parallel operation of transformers. A. Conducive of favorable conditions, which includes underneath conditions. 1. Voltage ratio and turns ratio be the same. Percentage impedance and X by R, that is inductance reactance divided by resistance, ratios be the same. Number 3, kVA ratings be the same. Number 4, position of tap changer be the same. These are the standard method of connecting transformers in parallel. Transformers of different parameters can also be possible to connect in parallel, but optimal control application that might not be fulfilled. And number B is the mandatory conditions. 1, must have the same vector group. Number 2, must have the same polarity. Number 3, must have the same phase sequence. Number 4, must have the frequency same. Now discuss with voltage ratio and turns ratio be the same. Transformers connected in parallel whose primary windings are connected to source bus bars and secondary windings are connected to the load bus bars. At the paralleling units, all the paralleling units must have the same voltage on the primary and the secondary winding terminals, that is their turns ratio must be the same. As the terminal voltages of both primary and secondary are to be the same for the parallel transformers, so their impedance drop that must have to be identical. So in that case, under any condition of load, the division of current that will be such that the product of impedance and current in one transformer would have been the same to the product of impedance and current in others. Paralleling transformers, if the voltage ratings are not the same, then there will be flow of circulating currents in both the primary and secondary windings, even at no load conditions. Turns ratio of a transformer that would have to indicate the difference in voltages between the primary and its secondary windings. In transformers having with a small voltage transformation ratios, the turns ratio is usually equal to the voltage ratio. Again, I repeat, in transformers having with small voltage transformation ratios, the turns ratio is usually equal to the voltage ratio. But for transformers with higher voltage transformation ratio, the voltage ratio may be different from the turns ratio. Such incidents would have been caused due to have a number of factors such as leakage inductance, copper losses within the transformer, and interwinding capacitance. Paralleling transformers, if that would have to exhibit the same voltage transformation ratio, but their turns ratio would have been something different, then circuiting currents must be flowing between the transformers even at no load. We have already seen, we have already explained. Due to low resistance of the transformer winding, the currents that circulate would have been quite large, causing a sudden failure of insulation. As of the loading conditions, there would have to require certain adjustment of voltage levels through the application of auto tap changing devices. Any sort of unequal tap positions will typically have unequal no load voltages, causing a circulating current to flow through the parallel connected transformers. Circulating current is thus being produced by the connecting transformer with having higher tap position, that is, of higher no load voltages, while the transformer operating with lower tap position, which corresponds to lower no load voltage, would have to receive consequential circulating current. The resultant effect of the producing circulating current as corresponds to the transformer with higher tap position would subsequently be added up with its load current. While for a transformer receiving circulating current that would have been subtracted from its load current, while for a transformer receiving circulating current that would have been subtracted from its load current. Working personnel must therefore be serious to understand the subsequent effect of circulating currents during the operation of the paralleling transformer's load sharing process. Paralleling transformers having different types of connections, type of connections, KVA rating, equal loading, unequal loading, concern over overloading, concern of overloading, circuiting current, recommended to connect. Now, type of connection, same percentage impedance and same turns ratio. But KVA rating, condition 1 is same. Then equal loading, yes. Unequal loading, no. Circuiting current, no circuiting current. Recommended to connect, yes. While there is unequal KVA rating, then equal loading, no. Unequal loading, yes. Concern of overloading, no. Circuiting current, no. Recommended to connect, yes. Type of connections, unequal percentage impedance and same turns ratio. Then KVA rating, if it is same, equal loading, no. Unequal loading, yes. Concern of overloading, yes. Circuiting current, no. Recommended to connect, no. For unequal KVA rating, equal loading, no. Unequal loading, yes. Concern of overloading, yes. Circulating current, no. Recommended to connect, no. Type of connections, unequal percentage impedance and unequal turns ratio. For same KVA rating, equal loading, yes. Unequal loading, no. Concern of overloading, yes. Circuiting current, yes. Recommended to connect? No. For unequal KVA rating, equal loading? No. Unequal loading? Yes. Concern of overloading? Yes. Circuiting current? Yes. Recommended to connect? No. Connecting transformers that are to be characterized through their turns ratio, percentage impedances, and X by R ratios. That is inductive reactance divided by resistance. During paralleling operation of transformers, these parameters would have been directly responsible for maintaining their corresponding efficiency and load sharing capability. If the stated parameters that would have been the same for all the connecting transformers, then maximum efficiency and optimum load sharing capability can be achieved during paralleling operation. With the same parameters that has to impose in equal load sharing and no involvement of circuiting currents in windings of the paralleling transformers. Any mismatch of these parameters that would have to create either circuiting currents or unwarranted current division within the transformers operated in parallel. Say, short circuit impedance. While transformers are suggested to connect in parallel, then the voltage regulation, load distribution, and short circuit current that are to be determined on their respective short circuit impedances. The short circuit impedance is the percentage of the rated voltage to be applied at the primary coil of the transformer for having rated current to circulate, keeping its secondary coil under short circuit conditions. The percentage of impedance voltage when the transformer is running at full load is related to the capacity of the transformer. Transformer of higher capacity should have the larger impedance voltage percentage. Transformer of higher capacity should have the larger impedance voltage percentage, whereas transformer of lower capacity that would have the smaller impedance voltage percentage. Impedance of the transformer is expressed in percentage as because it signifies the voltage drop on full load due to the winding resistance and leakage reactance expressed as a percentage of the rated voltage. Again, I repeat, impedance of the transformer is expressed in percentage as because it signifies the voltage drop on full load due to the winding resistance and leakage reactance expressed as a percentage of the rated voltage. The higher the percentage of impedance voltage, the higher will be the regulation. The higher the percentage of impedance of voltage, the higher will be the regulation. The lower the percentage of impedance voltage, the higher will be the short circuit current during short circuit condition. Again, I repeat, the lower the percentage of impedance voltage, the higher will be the short circuit current during short circuit condition. Group of transformers, while operated in parallel, it is rather obvious that their individual performance reliability that would perhaps being affected due to deviation of any of these parameters causing certain failure of proper paralleling condition between the connected transformers. It is important to note that whenever the no-load circulating currents in any of the connected transformers that would have to exceed 10% of the full load rating, then the particular transformer must have immediately be excluded from the group of paralleling transformers. Again, I repeat, it is important to note that whenever the no load circulating currents in any of the connected transformers that would have to exceed 10% of the full load rating, then that particular transformer must have immediately be excluded from the group of paralleling transformers. The IEC 60076 standard has clearly indicated the underneath guidelines of maximum impedance tolerance level for power transformers based on their rated power and voltage level. A. For transformers rated up to 500 kVA, the maximum impedance tolerance is 10%. B. For transformers rated between 500 kVA to 2 MVA, the maximum impedance tolerance is 7%. C. For transformers rated above 2 MVA, the maximum impedance tolerance is 5%. That is 10%, 7%, and 5%. 10% for rated up to 500 kVA, 500 kVA to 2 MVA, maximum impedance tolerance is 7%, and above 2 MVA, maximum impedance tolerance is 5%. The impedance of the transformer would have been higher than that of the specified value, then several problems as follows might have been imposed in the power system. One, higher impedance that leads to higher voltage drop across the transformer winding, which in turn reduces the voltage applied to the load. Higher impedance that leads to higher voltage drop across the transformer winding, which in turn reduces the voltage supplied to the load. Number two, the load is thus to operate at a lower voltage than the required one, leading to reduced efficiency with increased losses. Number three, the higher impedance that must have to instigate more heating of the transformer winding, causing an inevitable thermal overload, and due to have prolonged overheating that may ultimately lead to insulation breakdown, arcing, and other faults. Number four, the higher impedance that can have to create voltage regulation problems. The higher impedance that can have to create voltage regulation problems in the power system, leading to over voltage or under voltage conditions. This has forced to affect the ultimate performance and reliability of other equipment in the power system, including motors, generators, and other transformers. The standard is to cover all power transformers up to a voltage rating of 765 kV and also specifies the single phase and three phase transformers, auto transformers, and reactors. D. Leakage impedance. Transformers having with slightest variation of voltage ratios if somehow made to connect in parallel, then because of the inequality of induced EMFs, electromotive force, in the secondary windings, that has to impose a flow of circulating current in the loop formed by the secondary windings under the no load condition. So for the leakage impedance is of an undesirable property as it degrades the voltage regulation of a transformer, that is, it reduces the secondary voltage under load. Points to be noted: for a transformer with higher leakage impedance, greater amount of current that is to be required for maintaining the code flux constant. Again, I repeat, for a transformer with higher leakage impedance, greater amount of current that is to be required for maintaining the core flux constant. Generally, in core type transformers, the leakage impedance is always be lower side, and for which any small voltage difference causing the circulating current to generate that might have seen of the much higher order than the normal no load current. Generally, in core type transformers, the leakage impedance is always be in lower side, and for which any small voltage difference causing the circulating current to generate that might have been of the much higher order than the normal no load current. E. Polarity. Polarity of a transformer that has to indicate the instantaneous direction of induced EMF in secondary. While transformers are going to connect in parallel, they must have to retain the same polarity so as to ensure that the voltages and currents are in phase and that are to be additive one. If the polarities are not aligned correctly, that results in a dead short circuit causing a potential damage to the transformers. If the polarities are not aligned correctly, that results in a dead short circuit causing a potential damage to the transformers. In the context of parallel operation of transformers, it is rather mandatory to have the same polarity of all connected transformers, which has made to ensure that there would have been no such flow of unwarranted circuiting currents in transformers. Hence, it is worth to note that polarity of the transformers needs to be checked before connecting them in parallel. F. X by R ratios. Inductive reactance divided by resistance. We have already discussed the following points. 1. Two transformers of having similar per unit impedances, if are being connected in parallel, then they will mostly share the load in the ratio of their kVA ratings. Two transformers of different percentage impedances can also be possible to operate in parallel. But in this case, the load sharing will not be in the ratio of their kVA loads. These 2 points are very important. Two transformers with equal per unit impedances but having different X by R ratios can also be possible to operate in parallel. Working power factor of a transformer that can be determined by the ratio of reactance current, sorry, ratio of resistance current to capacitance current of its insulation system. Again, I repeat, working power factor of a transformer that can be determined by the ratio of the resistance current to capacitance current of its insulation system. So, the working power factor value of a transformer would thus to depend on the level of its insulation dryness. In case a new transformer is made to connect with a old existing transformer of same rating and that to operate in parallel, then there may have the possibility to some difference in their respective X by R ratios. It may happen as because the level of insulation dryness in new transformer might have been much better than that of the old existing transformer. Hence, the working power factor of the old transformer would have been less than that of the connected new transformer. It is what to note that any changes in working power factor value of an operating transformer that can indicate increased levels of moisture or other contaminants in the insulation system. However, any difference in X by R ratios that perhaps has caused to happen one transformer working with a higher power factor and the other with a lower power factor than that of the combined output. Therefore, the two transformers that would have to operate at power factors different from the power factor of the common load. In this aspect, there would have to impose a different phase angle of currents carried by the two parallel transformers and for which the real power will never be proportionally shared by the transformers. The short circuit ratio X by R for transformers connected in parallel should be equal, and that has to ensure to operate all transformers at the same power factor. Again, I repeat, the short circuit ratio for transformers connected in parallel should be equal, and that has to ensure to operate all transformers at the same power factor, same working power factor rather. In this context, transformers are thus to share active power and reactive volt amperes according to their ratings. Conclusive points to be noted. 1. Transformers connected in parallel with having the same turns ratios, percent impedances, and KVA ratings would maintain an equal current division and load sharing on each transformer. Number 2, transformers, if connected in one common bus with having the same turns ratio, percent impedances, but different KVA ratings, then the current division that would have been entertained as corresponds to each of the transformer to only be loaded to its own KVA rating. Number 3, there will be no circulating currents as because the voltages, that is turns ratios, are the same. Number 4, transformers with having same percent impedance, that has to ensure that their terminal voltages are equal, and transformers would have to share the load according to their individual KVA ratings. Number 5, the secondary of these transformers as are connected to same bus, then sufficiently high circulating current that would have to circulate between the secondary windings and therefore between the primaries also, causing an unnecessary extra I square R loss. It is thus to understand that whenever two transformers of different voltage ratios are being operated in parallel with the same primary supply voltage, then there would have been difference in secondary voltages. Secondary winding, while are being loaded, a circulating current once generated will therefore be responsible to produce an unequal loading on the two transformers operating in parallel. Hence, out of the two, one of the transformer might have been overloaded. Number 9. Hence, in this situation, percent impedance would have been the key factor. Number 10. It is as because if the percentage impedances of the transformers which are operating in parallel are different, then the parallel operation is still possible, but in that case, load sharing will not be in the ratio of their kVA loads. Transformers connected in parallel with having the same turns ratios and kVA ratings, but of different percent impedances, then there must be of unequal load sharing. Number 12, this unequal load division that has to occur as of the basic feature of transformers where the current that would have to divide in inverse proportions to the impedances. At the instance of heavy loading, paralleling transformers of lower percent impedance can be overloaded and simultaneously other transformers of higher percent impedance would have been lightly loaded. Number 14. Similar type of happenings that would also have been exhibited while transformers are to be connected in parallel with having the same turns ratios, but of different percent impedances and kVA ratings. Most important. Number 15. In case if the transformers which are to be connected in parallel with having the same kVA ratings but of different percent impedances and turns ratios, then circulating currents that would have to flow. Number 16, in this situation, it is important to note that the imposed circulating current, which would have been completely independent of the load and sharing of load of the operating transformers. If transformers are to be fully loaded, then significant amount of overheating might have been caused due to flow of circulating currents. If the transformers which are to be connected in parallel with having the unequal kVA ratings, different percent impedances and unequal turns ratios, then the imposed circulating current would have to combine with the load current as shared by each transformer, and that is to be obtained as the actual total current in each unit. It is much more indicative that two transformers having their respective turns ratios are large, then there may have a chance of considerable error in their voltage configuration, even their turns ratios are the same. As of the perception, if the voltage ratio is not the same, so The secondaries of the paralleling transformers will not show equal voltages even if their primaries are connected to same busbar. Any deviation of voltage parameters in secondaries that would have resulted to impose large circuiting currents to flow in secondary windings of the transformers. Number 22, as of the consequential effect, there would have a reflected circuiting current on the primary side also. Number 23, even without connecting load, there will be considerable amount of current that would have been drawn by the transformers, causing an unacceptable copper losses. Number 24, flow of circuiting current in the loop formed by the secondary windings under the no load condition would have been quite high, as because the leakage impedance is low. Number 25, in two identical transformers having percentage impedance of 5%, and if they are possessing a no load voltage variation of 1%, then that will impose to flow circuiting current of 10% of full load current. Once the secondary winding are connected to load, this circuiting current gets added to the load current and will tend to produce unequal loading of the two transformers. Perhaps there may not be possible to entertain the full load from this group of two parallel transformers, and as of the consequence, one of the transformers may get overloaded. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.